Let's use VBAR. So we are talking about CQ lookup. CQ means catch the quotients. For this idea, you will it's the central innovation for CQ lookup, and you will see this at the end of the sharing. So first, we will look up the how it works for the CQ lookups. Say what lookups do is to find the f belongs to t if f belongs to f n, t belongs to f capital N, and if n is less than capital N. If you can prove that f belongs to t, then you can say this lookup how it works. But for CQ lookup, it uses a lemma for this kind of lookup. Lemma is you have this sum x to n I'm I have x to ti equals to fi. If this sum equality is satisfied, then you can say f belongs to t. So I'm here is the times for fi in t. I'll give a simple example for this. For t, we can make it as 1, 2, 3, 4, 5 to n. Then f will be, let's say, 1, 2, 4, 4, 4, maybe 1, 2, 2. So we can say f less than t here, and m, we can see m here, m1 will be, so 1 only shows ones here, so m1 will be 1. m2 will be, there are 2, so it's 2. m3 will be 0. And m4 will be 3, right? And m5 will be 0. Then mn, they are all 0. So then we can calculate this. This will be left hand side, this will be right hand side. Left hand side will be x plus t1 is 1, m will be 1, plus x plus 2 will be 2, then 3 will be 0, so this one will be 0. Then x plus 4, 3, right? And then all of them are 0. So finally, this one will be x plus 1, x 2, 3, right? And the right-hand side will be, so here will be x plus 1, 1, and will be 1, and the same, you add them for twice, so it's, and then 3 will be 0, 4 will be just multiply for 3 times. So then the final result will be equals to left hand side. So that's the intuition for this sum equation, and for this kind of lookup, you can prove that F belongs to T. So far, any question? M is the times for this element shows in here.
Oh, okay. I see it.
So far, good, right? Okay, so the call is for this equation. Then we need to demonstrate some checks. There will be 3 checks. The first one is 3 checks. So the first one will be the left-hand side check. This is not a polynomial, but we can convert it to a polynomial later. But we need to check that this this side is correct. Prover cannot cheat, and also for the right-hand side. So we need to check the left-hand side is correct, and same as for right-hand side is correct. And the third one is we need to check the equation satisfied. Is for the sum check correct. Okay, then actually this is not the central innovation for CQ lookup. We will talk about that. I put it at 0 at last is the optimization for this process. Okay.
So you said you mentioned 3 checks. Left hand side is correct, right hand side is correct. Do you mean that left hand side equals right hand side, or do you mean that left hand side?
It means itself.
The calculation is done correctly.
Yeah.
Okay.
So this optimization is done in pre-processing. Okay, let's start from the first one. How we check that? So here verifier will choose. So this one is your sum check for this left hand. So verifier just choose a random bit to use for to replace x and with later check. So after that we can assign AI equals to this So it will be beta plus ti mi. And there are multiple ai, so we can convert it to a polynomial. Ax equals to mx beta tx. Okay, continue to do this. Ax beta tx minus mx equals to 0. So I think this polynomial, you will be familiar how to check that. You will use the ax beta tx. We'll add a quotient polynomial and a vanishing polynomial. Use v. Okay, so far good. And then we can just do some simple just move them to the other side, so they are the same. And then we can use pairing for that. To check the polynomials is correct. So here is the bilinear pairing. I just first I write them down. Bilinear means that if you have E, here is plus, P, Q, R, so you can make them to E, P, R, E, Q, R. Yeah, so this just this form is this plus this, so it's the same form for that. Yeah, so this is just a pairing verification. Okay. So far, is there any questions? Okay. So I think the second, we'll go to the second, the right-hand check will be the same. We'll have I so I can verify with standard beta and then bi, then I can have a polynomial for this. Then I can continue to do this Q, B, okay. Then we'll have bx fx qb hx. And then we do the pairing for this. All right. Yeah, so that's the first two checks. Good, right? Okay, I will erase this because they are similar. Okay, let's go to the third one, some check for that. Their dilemma for this is so you will get this result if x belongs to H. H is a multiplicative subgroup of F. Okay, I will give a simple example for that. So in the opening, I give an example for the roots of unity or that H equals to 1, 8, 12, 5 for F13. And if we choose a simple fx equals x plus 1, then we can calculate this. Then the left-hand side will be so you will notice 5 and 8 is 0, right? Because it's the 13. 1 and 12 is also 0, so this one will be 4. We only have this for 1. And the right hand side is t will be 4. F0 x is 0, so x0 is 1. They are equal. So that's another lemma for this kind of calculation. Let me check the notes. Okay, I see. So to check this equation, we need to convert this to, so this one will be A, right? So we just need to check the equality for n A 0 equals to n B 0. Yeah, so we convert that problem to this problem, right? So this one is important.
Which problem again?
So the third check is to check this. They are equal. So we convert this problem to this problem because we have this lemma. Yeah. You see, this one is the sum, and this one is the polynomial. Okay. So do I need to write down the intermediate steps? Okay. So the left-hand side, so here will be, you convert to AX, right? So AX will be the FX. So, okay, let me write down, this is I belongs to N A.
In the subject one, H is multiplicative subgroup of what? F, right? That is F, right?
F, yes. Yeah. So this one will be AX, right? So if N is a multiplicative subgroup, we can replace maybe the same H. So A is the FX. So we just need to calculate this, maybe just use N. And okay, we move it down. X equals H, F X equals T, F 0, right? So you can see the relation for them. So here H, the size of H is T, H, T. So this one is just N, right? Oh, like this form is, I think it's clear. So we just move N here, A 0, right? So we have this, correct? We have this.
Okay. Oh, this. Okay.
Yeah. So this is from here. So yeah, it's the same. So we get the left-hand side, final get this one, and the right-hand side, because the size of that is lowercase n, so it's like this, right? Okay. Actually, because these two n are known by public, so we just need to prove they are correct. And also, this point to evaluate is also known, so we only, and also this polynomial is known, so we only need to check these two polynomials, evaluate the correct value. And this will convert this kind of issue. You will have a polynomial and you use pairing to verify that. So I think I don't need to cover that. And finally, I think this sum check satisfied. Pairing, verify by pairing. Okay, so that's all these 3 checks. So is there any question for that? Okay. So then we talk about the optimization part. Is there a time limit for me?
5 hours.
Okay. We can see. Okay, this. You can see this. If we calculate this quotient A, it will be, I think, should be O n squared. So this paper is talk about how to optimize this. It uses cached quotients. Then, okay, I will show you how to do this. We have AX. We just put this one here. TX. So actually, you can treat this as a remainder for another polynomial. So this one will become and then we have AX equals to LIX AI. So this is the Lagrange interpolation. And also there's a lemma for this equation Tx. This equation you can see from this is just to check Tx value in each point. The value is Ti. I think I can make some change for this. We LIX. We move this here, it will be Tx. So this form you guys should be familiar is quotient I'm managing to verify Tx value is Ti in each I, right? So it's just a transform to that. And then we can calculate this one with this 2 will be ax tx equals to this one so tx times li will be this. So we can keep doing that. TILIX QIX JVX. Okay, we finally get this. If you look at this equation and look back this one, so you both have the way, then QA will be this and RX will be this. QAX will be this. QI. And RX AI TILIX. Okay, so there's a way to calculate this kind of QIX because you only need to choose from each. You only need to pre-process this capital N for QIX. So the pre-process will be N log N to get quotient A. And check. No, this one will be N log N. it says that actually this you don't need to this n. You can just use lowercase n to do this calculation. So the plural only needs O n log n to calculate this. Okay, I think I better stop here to skip the processing side, because there is also other, maybe I will share that next time.